Hi there, folks. This is the practice chapter 12A review test. And as always, I am the amazing Mr. Jansen. So away we go. If we take a look at these first couple, we're looking at some definitions that we talked about throughout this chapter and throughout these couple sections. First one says quartiles separate data into blank equal pieces. Remember, quartile comes from the word quarter, which means 4 equal pieces. So we split this into 4 equal pieces. And think about a box and whisker plot. You know, we've got a whisker, and then a piece of a box, then another piece of a box, and then another whisker. It's 1, 2, 3, 4 equal parts. Okay? Each value in a set is called an element. Remember, we talked about this when we talked about matrices. Each value that's in there we call an element. For percentile, percentiles separate data into 100 equal pieces because remember, percent literally means out of 100. So when we're talking about a percentile, we're breaking the data into 100 equal pieces and then finding the percent value that goes with that. Blank is a graph in which there are no gaps and intervals do not overlap. Remember, when we talked about intervals, we were setting up frequency tables and we couldn't have any gaps and we couldn't have any overlap. And the graph of a frequency table is called a histogram. And that's how we graph frequency tables. We use a histogram. The next one it says is a rectangular arrangement of numbers. That's just a matrix. Remember, a matrix is when we put these things in a rectangle with the brackets around it. So that's our matrix. And then the last piece of this also deals with matrices. It says a real number factor is called a scalar. Remember, we use scalars to multiply by a matrix, and that's when we multiply each piece of the matrix by the number on the outside. Take a look at these next two. I'm adding or subtracting the matrices. If I look at the first one, it's just simple addition. So remember, I add things that are in corresponding positions. So like the -2 and the -3, those are in corresponding positions. They're in the same spot in regards to where they're positioned in the matrix. So I'm going to add them together. -2 plus the -3 is a -5. And then if I look at like the 5s and corresponding positions to the -2, so 5 plus a -2 is a 3. The -1 plus the 11 is a 10. And then the 7 plus 0 is a 7. So when I add these two matrices together, again, I add the corresponding positions, and that's my final matrix. Number 8, we're going to treat just like number 7, but we have to tweak it first. Instead of doing subtraction here, my recommendation is to do adding the opposite, just like we would any other time. So with this one, instead of subtracting, I'm going to add the opposite, and I have to do the opposite of everything that's inside this matrix, okay? Because I'm going to be subtracting each of those values, I can change each of them to adding the opposite, and now I'm just going to add the corresponding positions just like I did in number 7. The -5 plus the +12 is going to give me a -7. Down here, the 6 plus the -12 is a -6. 4 plus a +4 is a +8. And then -9 plus the -8 is going to be a -17. And that's it. That's all there is to it. So again, change it to adding the opposite, and then we add the corresponding positions. For these next two, we're doing some scalar multiplication because we're multiplying by this constant value on the outside. Remember, with scalar multiplication, essentially what I'm doing is my distributive property. So I'm just going to multiply each element inside the matrix by the scalar that's on the outside. So here I do 3 times the 5 for my first position, that's a 15. Then I do 3 times the -2 is a -6. 3 times the -6 is a -18. And then 3 times the 10 is a 30. And that's my new matrix. So I multiply each element by the scalar on the outside. Number 10 is very similar. I've got a different sized matrix. But again, I'm going to multiply each element inside the matrix by the scalar that's on the outside. So -4 times the 2.5 is going to give me a -10. -4 times the -8 is a +32. And then -4 times the 3 is a -12. And that's it. Okay, so multiply each element by the scalar. For this next one, the first thing we want to do is write these numbers in order. And I've already done that. So if these are the predicted scores for the test that we're about to take, we want to create a frequency table, a histogram, a cumulative frequency table, and then decide whether or not this thing is uniform, symmetric, or skewed. And you don't necessarily have to write these in order to do this problem, but it helps. And so I've gone ahead and done that. I've written mine in order. And now I'm going to create a frequency table with intervals of 10. Okay, so I've got in my frequency table, I've got my score, and then I've got the frequency of that score. And again, if I'm going intervals of 10, I would start 70 to 79, that's 10 values, then 80 to 89, and then the last one we need is 90 to 99. And I just have to count these up. The scores that are from 80 to 89 are right here. Sorry, 70 to 79 are right here. There's 4 of them, so I put a 4 down here for the frequency. And then the 80 to 89 is where we're going to get the most. I just have to count these up. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 of those. And then the last section, the 90 to 99, I just have to count these up. 1, 2, 3, 4, 5, 6, 7, 8. Looks like I've got 8 of them. And that's it. That's all there is to it when I do a frequency table. The next thing I look at is the histogram. And when I draw a histogram, remember I put my intervals at the bottom and I put my frequency on the y-axis. So my intervals go down here, so 70 to 79, 80 to 89, and then 90 to 99. And for my frequency, I have to go as high as 11. I'm just going by ones here. 1, 2, 3, 4, 5. And now I graph each one. The first one, it looks like I've got a height of 4. I'll use a different color for this. So I've got a height of 4, so I put a bar that's 4 units tall. And then for the next one, it's 11, so I have to extend that bar up to 11. And again, there's no spaces in between. And then the last one is 8, so I come up here to 8, and I put a bar. Okay? And that's it. That's all there's to it. For number 13, it asks us to do a cumulative frequency table. And really, the first part of the cumulative frequency table is just a repeat of what we did in the problem right above this. Okay, so I'm going to repeat that portion of it. So again, I had the score here. Then the frequency, and now I want my cumulative frequency. Okay? And from here, I just write down the scores just like I did before, 70 to 79, 80 to 89, and then 90 to 99. I put down the scores, the frequency of each of those scores like I did before, 11, 4, 11, and 8. And now the cumulative frequency table is just like a running tally. So from 70 to 79, there's a total of 4. And then after I include the 80 to 89, there's the 4 from the previous and the 11 from this section. So that's a 15. And now I tack 8 more on, which gives me a 23. And that's it. That's the only difference between a frequency table and a cumulative frequency table, is that we put one more column down that keeps the running tally. And now for the last one, it says, would you describe the histogram above as uniform, symmetric, or skewed? And really, this one, we could make an argument either way. I'm going to say you could call it symmetric because the peak is in the center. And it looks like the end two pieces are about the same. Or you could even make an argument here for skewed because that last column is so much higher than the other that most of my values are towards the top than it is anything else. Okay? For these three, we're looking at which central tendency works the best, which one describes the data the best. If we look at number 15, this is the one case where we're going to use this measure of central tendency. Since almost every value is the same, I'm going to choose the mode here. And again, that's because almost every value are the same. And this rarely happens. And in fact, this one you could choose the median for this one because the median would give you the same value. And typically that's what happens when the mode happens to be the best choice, which is why we typically choose the median. The reason we don't choose the mean is because there's an outlier here of 500. Okay, so don't choose the mean if there's an outlier. The mode will only happen if almost every value is the same. In number 16, again, the outliers are what's really important here. So if we look through here, we see that there's an outlier of 81. Since there's an outlier, it means that the mean is not a good choice. Whenever there's an outlier, we want to go with the median. Okay, so we're going with the median because there's an outlier. Okay. And then for number 17, we look through here. I don't see any outliers, and it looks like the data is pretty evenly spread. So with this one, we're going to go with the mean. And again, it's because there aren't any outliers this time. The mean is usually our choice unless there are outliers. Okay?